Now we're doing 2 learning goals today. They're both pretty easy, and they're both going to be on the AP test, and they're both easy points that you need to guarantee yourself easy points. So these are 2 points you get on the AP test automatically because it's so easy. And we need to know.
What if I flood it?
We need to know what it's asking, and we need to make sure we know how to get it. So our 2 learning goals are, we're going to approximate the instantaneous rate of change at a point using a graph or table. And the other one is, we're going to approximate a function value using a tangent line. Those are the 2 things we're going to do. So on this number 2, the part we're interested in is part A. So we're interested in part A of this problem. Alright, the prompt says the temperature in degrees Celsius of the water in a pond is a differentiable function W of time t. So what did they just tell me about W? It's differentiable and continuous. Very good. The table above shows the water temperature as recorded every 3 days over a 15-day period. Now, anytime they tell you something is differentiable, what should we know we should be able to do?
It's
IROC. MVT. Whenever you see differentiable, you need to think, if I need to use MVT, I can. Okay? So when I see differentiable, I'm going to label it. I can use MVT if I want to. Okay? I'm not going to have to in this problem, but that's something we need to get to. All right. It says, use the data from the table to find an approximation of W prime of 12. So the computations that lead to your answer indicates units of measure. What does W prime of 12 represent? IROC at 12. Okay? What is this table of, though? W. This table is W, and I want W prime of 12, which I cannot do from a table. But there's something I can do to approximate W prime of 12. And what do you think that something is?
IROC.
IROC. If you're going to approximate an IROC, you're going to do it with an IROC. Okay? So what I like to do is 12 is what we want. So I like to use the points on either side of it to do my IROC. So I'm going to do W of 15 minus W of 9 over 15 minus 9. So W of 15 is what? 21. W of 9 is 24, and 15 minus 9 gives me 6. So we end up with negative 3 over 6, which is negative 1/2. So I'm going to say W prime of 12 is approximately negative 1/2. Now, what about units? And there are 2 ways that we can think about getting the units on this.
What are the units of W?
What are the units of W?
Celsius.
Degrees Celsius.
Per day.
Tells you that, right?
I can't see it.
You can't see that? We got desks up here. You can sit right there.
Well, I knew what it was.
Thank you.
You know what it is now.
All right. So, what are my units of W prime of 12 and what?
Degrees Celsius per day.
Degrees Celsius per day. All right. So, what were you thinking to come up with that, Logan?
The derivative is always something over time.
All right. So, if I start out at degrees Celsius and I take the derivative of something that's in degrees Celsius, I have to end up with something that's degrees Celsius over a time. So my time in this problem is days. Now, what's the other way of thinking about it?
Something about the above.
It's changing. So
I would say, look over here back at IROC. What does that represent? Degrees Celsius. What does this represent?
days.
Days. So degrees Celsius per days gets me the same place. So either way, that's how you can get to your units. Okay, one of those 2. Now, this is the way I recommend you do it whenever they're wanting you to approximate an instantaneous rate of change, is use the point before and the point after. However, there's another way, or some other things that are acceptable. So if I want an approximation for 12, I can use the one before it and 12 itself, or I can also use 12 and the one after. So if I wanted to, I could do W of 12 minus W of 9 over 12 minus 9. I could also do W of 15 minus W of 12 over 15 minus 12. Those are also acceptable ways of approximating.
All those numbers will be different.
Oh,
All those numbers will be different, that is correct.
I thought you're having to do two IROCs.
So what?
No, I'm saying you can do the one we did, you can do this one, or you can do this one to approximate an instantaneous rate of change.
How's that the
Which
same?
is the best
It's
one?
not the same.
Is one better
will
than
be-
the other?
I recommend the first one we did because when you look at the scoring rubrics, that's the way they do it. They do it with the one above and the one below.
You'll get the same.
So when you match exactly what's on their scoring rubric, it's easy for them to grade. And they'll grade it and move on. Okay? You're causing them to think a little bit more when you give them something like this.
But you're saying each of those gives you different.
Each of those gives me different values, that's correct.
But it's
It's
an
just an
approximation.
It's approximation.
What's the range that you can?
You're going to do one of the three things we did up there. You're going to use the one above and the one below.
Put on the test.
On the test, you've got three options. You
I
can
know,
do-
but what's the range of how much you can miss a number on the free response?
You can't. You got to do everything right.
If you're not missing a number, those are options.
You would have three. There's three different numbers they'd be looking for.
Okay.
One for each one of the possibilities. That'd be it. All right, now. This isn't related to what we're doing today, but I want to go ahead and think about it. And I mainly want to talk about that part right there.
IROC.
Says approximate the average temperature. What would we do to approximate average or find average temperature?
I don't know how to think about that.
Function above temperature.
The function above temperature over
Time.
time. So I want the change in the function above temperature over the change in time. So what is my temperature function? W. W is my temperature function. So I want the change in the function above W over the change in time. Okay, we can't do that right now, but we can at least know what we need to do to get average temperature.
Why can't we do it?
Because right now we don't know how to get to the function above. But we're getting ready to learn something when we get back to Christmas
derivative of it?
that will allow me to get to the function above.
That'd be like speed.
It's only
Is it derivatives of it?
No, it's called the integral of it. Integration goes up, derivatives take you down. So if you want to go back up, you got to integrate. If you want to go down, you got to take the derivative.
What is T?
What is
Is
T?
Is that above or below?
T is not a function.
These are hooked up according to the alphabet.
So we need to find velocity. That's where the whole block is.
Alright, so that's the first type. That's the first type. What are we going to use to approximate an IROC?
IROC.
IROC. That's the first type of problem. Next one. Okay, and on this one, we're interested in answering part B. It says let y equals f of x be the particular solution to the differential equation with the initial condition f of 1 equals negative 1. Which you don't need to worry about that just yet. It's mainly the second line. Write an equation for the line tangent to the graph of f at 1, negative 1, and use it to approximate the function value of at 1.1. That's what we're going to do. So let's take it in parts. We should be able to do part 1 very easy, because what is it asking me to do? Write a tangent line, correct? And what do we need to write a tangent line?
And a polar slope.
We need a point and a slope. Did they give me the point?
Yeah.
Yes, they gave me the point. So y minus my y value equals my slope I don't have yet, and x minus my x value. So I can do that real quick. So now I need to get the slope.
Oh, there it is.
How do I get the slope?
IROC.
Point slope.
Derivative.
Derivative. What about the derivative?
Same on slope.
Alright.
Let the derivative.
Do I have the derivative?
To IROC.
No. Yes.
Yes, I have the derivative.
It's
They gave it to me.
negative
dy over dx equals negative 2x over y. That's the derivative, correct?
Yeah.
How do I know that's the derivative?
Like,
The dy over dx tells me it's the derivative. So what do I want to do to get my slope?
plug
Plug
in
in
for
x
x
and
and y.
Plug in 1 and negative 1. So negative 1 in for the y and 1 in for the x. So that gives me negative 2 over negative 1, which gives me
That's
a
IROC.
slope of 2. It is IROC. What is it I'm trying to find?
It's always IROC.
Slope at that point.
Slope at that point, which is the tangent line slope, and how do we get a tangent line slope? IROC. So it is IROC.
You do right.
Alright, so there's the first part. The second part says we want to use it. We want to use it to approximate f of 1.1. So what do you think we want to do to use the tangent line we just wrote to approximate f of 1.1?
Plug in
Plug in 1.1 for
x.
x. That's all we got to do. So y plus 1 equals 2, 1.1 minus 1. So this would be 2 times 0.1. So I'm going to have negative 1 plus 0.2, which gives me what?
Negative 0.8.
Negative 0.8. So I'm going to say that f of 1.1 is approximately negative 0.8.
Why is it approximately?
Because how did I get it?
By
I
approximate.
used the tangent line. I didn't use the actual function. If I'm using the actual function, then it's going to be the exact value.
Okay.
But in this case, I used the tangent line to find it. So since I approximated, I got to put squiggly lines. Okay, and notice how close is 1.1 to the x value of 1? Very close. Why do you think they did that?
Plug mine in.
To get more exact.
To get more exact. How do I get more exact that way? Brock?
I was prepared for a follow-up question.
Alright, so let's say I've got this function right here. And let's say that right here, right there is my x value of 1. Which means its tangent line is going to look something like that. Now, how close is 1.1 to 1? Pretty close. So that means that the tangent line value I get, the tangent line approximation, how close is that going to be to the actual value?
Pretty close.
Pretty close.
Pretty close. Now, what if I use an x value that was over here, such as 3, and got an approximation for 3?
Way off.
That approximation would be up here when the actual one is right there.
So I didn't understand the tangent line was even close.
So that's why they're using 1.1, is because if I'm very close to an x value, that means my value should be very close to the exact value. So that's why they're always going to give you a point that is extremely close to the point you're using.
Why all those dots?
They're just so close.
That has to do with the slope field we'll get to later.
For this question, we
That
didn't
looks
use the
enjoyable.
graph really.
I love
Right? What?
Did we use the graph?
No, we don't need.
In the test case, it's just gonna color.
All we need for this one is part B and then the derivative that they gave me. Now, what can you tell me if I use this tangent line that's in red? If I use that tangent line, how are my approximations related to the actual values?
They're closer or
Are they bigger or smaller?
bigger
They are bigger. Why are they bigger?
because it goes on top.
Because what's on top?
Tangent line.
The tangent line is on top. Okay? So what if I chose a point over here and I did a tangent line, and then I used that tangent line to approximate my values? Would my values be bigger or smaller than the actual values?
Smaller.
Smaller. Why?
Well, they're always small, would they?
Tangent line is under.
The tangent line is under the curve here.
Oh.
Okay? What can I do? What's going on with my graph at these two places that I would be able to tell whether or not my tangent line would be below or above? What's going on? What's different about this spot and this spot? Very good. Concavity. This one is concave down. Where's your tangent line? Up on top. This one's concave up. Where's your tangent line? On the bottom. So the tangent line, the concavity will tell you whether or not your tangent line gives you an approximation that's too much or too little. All right. One more question real quick. This one doesn't take long. It's the easiest one of all of them.
That's an easy question.
did that for last time too. Alright, so they're giving me f of 2 equals 4. They're giving me f prime of 2 equals 1/3. They want me to approximate f of 2.1. So what am I going to use to approximate f of 2.1?
Tangent
The
line.
tangent line.
Yeah, jeez.
So it's going to be y minus what?
4.
4 equals something, and then x minus 2. What's my slope?
1/3.
1/3. Harrison, why is 1/3 my slope?
Derivative is the slope of the tangent.
Derivative is slope of the tangent line. So since I plugged 2 in the derivative, that means 1/3 is the slope of the tangent line. So now to approximate 2.1, all I have to do is
Plug in 2.1.
plug in 2.1. When you do that and solve to save time, you end up with 4 and 1/3.
Awesome.
So, how do we approximate an IROC?
A-Rod.
We use an AROC and then write the equation of a tangent line and then use that to approximate. Pretty straightforward.